Hi everyone, my name is Sahaya. I'm designing electronics for Flipper Zero, and today we're going to design an external module for Flipper Zero from scratch. Beginners who are accustomed to such breadboards made of a bunch of wires may believe that PCBs are way too difficult for them. But in fact, designing your own industrial-grade PCB is nothing impossible, and today I will show you how to do this in Altium Designer. On its side, Flipper Zero has a GPIO header on which various data lines, power, and SWD debug interface are broken out. On pin 10 we have clock, and on pin 12 the data line. Flipper itself is flashed and debugged for these contacts, and we will design an external module that will connect to this GPIO header. Flipper is built on the basis of the STM32 MCU. These MCUs are flashed and debugged via SWD using the ST-Link board. Personally, I usually use this ST-Link V3 Mini, but you can just insert it inside Flipper, and its cable also doesn't match the GPIO header. So we're going to design an external module which will have a built-in ST-Link. Here you can see the final design of our external module. On its right side you can see a built-in ST-Link, and lines that are used to debug the controller are broken out to these pins. In order to understand how we're going to design this, let's look at the ST-Link datasheet. Let's scroll to the pinout. And here we can see that the SWD we need is on the 4th ST-Link pin SWDIO, and on the 13th pin SWCLK. So we will have to connect these lines to the 12th and 10th pins of the Flipper header accordingly. It's going to look like this. Also, we will connect the grounds and the rest of the pins to our module. Let's start up Altium Designer and create a new project. File, New, Project. Name the project, for example, ST-Link Flipper. Select the path to save the file. I will leave it by default. Click Create. We have an empty project. Let's add the schematic file for our circuit diagram. Let's create one more PCB file straight away. And here we will be designing our PCB. Now we need to save everything. PCB doc. Let's also call it ST-Link Flipper. And save the SCH-doc file too. It should be taken into account that PCB-doc and SCH-doc, like all entities related to this project, must be stored in the same folder. Here we have an empty circuit diagram. Let's sketch out our future circuit. Let's select components, and I already have a pre-made library with components for Flipper. It's free to use and modify, and you can download it on Flipper's website or follow the link in the description. Let's drag the components to the schematic. I placed the default PLS connectors with a step of 2.54 mm on the schematic. Here on the right panel you can see a 3D model of this component with which we can connect to Flipper. We can see that the pins are labeled exactly the same way as on Flipper. Let's drag ST-Link here too. Accordingly, we now have a GPIO header with signed pins. And on the right we have ST-Link, and everything matches the pinout in the datasheet. Let's start with power. Select the power port tool, press tab, and sign it accordingly to the pinout, 5 volts. Select the symbol that suits us, for example an arrow. You can rotate it as any object using the spacebar. Let's rename it to 3.3 volts so that everything matches the pinout. We can also add the capacitor on power lines. Make sure you're using the grid, otherwise you're going to suffer just like I do. Press the G key. Here in the corner you can see the grid settings. Let's change it from 100 mil to 50. So we put capacitors, connect to the ground. All the ground pins must be connected to this port GND. Let's do the same on the ST-Link side. And all that's left now is to connect the SWD. You can connect it directly, but I usually don't do that because then the circuit often becomes completely illegible. What I do is I connect the contact with a piece of wire and assign net label. Place net label. Name net label in accordance with the pin. You can select multiple objects by holding Shift and selecting multiple objects. Let's copy and paste it into the same pin. Thus, in our diagram, these SWCLK pins and the 13th pin are now logically connected on the diagram. And also on the PCB, they will be connected by an electrical track, since they have the same net label. Let's do the same with the rest of the pins. Also, Flipper has SWO on its header, and it is also broken out on ST-Link, so let's connect them. Let's copy these parts, insert them here, rename net label. Also, different signal lines are broken out on the external pins, and we want to make them available on our board, so let's also connect them using net label. Otherwise, Altium will be unable to use them on our PCB. Let's break them out on our board so that developers are able to connect to these pins too and make use of them. Now let's do the same with the external ST-Link pins. ST-Link also has UART available on its external pins. It works like a normal USB UART adapter. So we will connect it to Flipper's UART. It's also broken out on the header. So let's connect TX and RX. You can make it look better if you feel like it. As you can see, ST-Link has lots of different interfaces available besides SWD and UART, SPI, I2C, and so on. Let's break them out on our board too. But I'm not going to connect it to Flipper. I will just leave it there for developers so that they can also make use of these pins as they see it. You can see that we have our components labeled as X question mark. All of them. We need to make them possible to identify. Let's number all these designators. Tools, annotations, annotate schematic, update, OK. We have the schematic ready. Let's perform its validation. This will check for any errors in the schematic. Altium does it automatically. Press the right mouse button and select Validate. We can see a lot of errors. Altium says that this pin, for example, is not connected to anything. We have left them floating on purpose, so it's not an error. And to make it so that Altium doesn't see it as one, let's place a generic no ERC marker here. This tells Altium that these pins aren't supposed to be connected to anything and that we are leaving them like that on purpose. Saved. Now we again click on the right mouse button and click Validate PCB project. We have eliminated all errors and our circuit is ready. We can now convert the circuit to the PCB layout, so let's do it. Design, update PCB, validate. We see that some footprints have appeared. These are exactly the footprints of the components that were displayed on our diagram. The red square here highlights the room, meaning that those components are all located on the same schematic sheet. Let's remove the square. First, let's set up the working field. I will set the grid to appear in millimeters because I prefer it that way. We see a lot of green everywhere. This means that we have some kind of error here. Contact pads are located too close to each other. This depends on the design rules, so let's configure these rules. There are quite a few of them and each rule needs to be adjusted for specific production. But we're not going to do this now. We're just going to leave everything by default and make the gaps 0.2 millimeters. A 0.2 gap should be okay for any production. So let's have it like this. Errors fixed. And let's set the origin reference point before designing our board. Edit origin set. Let's put it somewhere random. If you press the G key, you can adjust the snap grid. Let's start with the board outline. Select the mechanical layer, mechanical 1. Select the lines tool and draw a rectangle equal to the width of the board. Let's open the drawing and take a look at Flipper's case. Case width is 99 millimeters. Let's make the board small enough that when connected with Flipper it doesn't go beyond this case. 18 millimeters should be fine. Let's make our board approximately 80 to 35 millimeters. Count 80 millimeters from the origin. In the corner of our work area, you can see that a certain number of millimeters is counted along x-axis. Also round off the edges of our board, press Shift Space and select the corners. The path should be closed. I probably have less than 80 millimeters here actually. Let's check. Click on Ctrl M. We have a ruler here. Yes, 78 millimeters, but I think we can leave it like that. You can do everything perfectly if you want though. So we have 25. I suggest moving it higher. You can do so by just changing the coordinates here. And let's make the width approximately the same as we agreed initially. The outline of the board is ready, and let's cut the board accordingly to this shape, so this whole black area will be cut off and only the board itself will remain. Design board shape, define board shape from selected object. You can press 3 and switch to 3D mode. And here we have this blank board. When you press 2, you will return to 2D mode. The next step is positioning the components. Switch to 3D. Let's transfer these components to the bottom layer. Our board has 2 layers, top layer and bottom layer. We are not going to change this step. Select the component and place it on the bottom layer using the Properties panel on the right. Thus, our PLS connectors that will be used to connect to the board will be located like this. It's important to take into account the distance between the headers so that we can connect to Flipper properly. Let's open the schematic and see what distance should be. The distance between the centers of these extreme pins is 17.78 millimeters. So we should set the headers counterparts at the same distance accordingly to make it simple. Let's set our starting point in the middle of this pin and count 17.78 millimeters from this point. Here's what we have, but I'd like to center it. Select 2 components at once, and using arrows we can move them left and right along the x-axis. Let's check so that the distance between these pins is exactly 17.78 millimeters. Shift-C removes these tool tips. Now only ST-Link remains. Let's put it in this way, because Flipper's cable will also be directed to the right. And also, almost everything that is connected to the ST-Link is located on the right side. These thin lines indicate connections between paths of different components. These are the same lines that we connected using the net label. Let's add capacitors. And now we're going to fill all this empty space with metallized holes to make it possible to solder some headers to it. On the Properties panel, set the dimensions to 1.56 millimeters. Make them the same as in our header, 1.56 and 0.9 millimeters for holes diameters. Here it is necessary to take into account that the step of these headers is usually 2.54 millimeters. Therefore, we will place those holes at the same distance from each other. You can arrange them like this using the coordinates, but this is way too time-consuming, so you can just select the component, Ctrl-C, and copy it using the next pad as a reference. You can copy the group of components, Ctrl-C. Now using, let's say, this next pad as reference, place the holes like that. So we placed everything, and as you remember, we wanted to break out all these signal lines on our board. You can select this component, for example, and assign the line, let's say 5 volts. This thin line appears, which means the connection between these pads. That said, we just want to extend them up, all these pads, so that we can solder to them separately. So let's assign the lines to all these holes. And if you press Shift, all these identical lines we have are highlighted. Now, using the Interactively Road Connections tool, connect them all using wires. And now these holes are physically connected with the conductive track. Next, we will start to build tracks to ST-Link. Let's start with the SWD, hold Shift and see that the pad that we need and to which we need to build the track is here. Let's also build a track to ST-Link clock. At some point, it may turn out that we can't build the track because these conductors are in the way. So we need to relocate the electrical track to another layer. As you remember, we have 2 layers. Press 2, a via appears, and then press L. We see that the track is now on another layer because it's now blue according to the color of the layer. We can also optimize the wiring layout. Let's switch to the bottom layer and connect UART TX on the bottom layer. It turns out that the layout of the lines is not exactly optimal. You personally can spend some more time and make it better. It all depends on your imagination and precision. I didn't connect the ground to anything yet. In the end, I'm going to fill everything with polygon, and these GND pads will automatically connect to the ground polygon. This is enough to flash STM32, which is installed on Flipper. But we also assigned netlabel on the diagram for ST-Link. As you can see, those pins that are without netlabel, without a line, they are displayed simply as contacts, second and third. All these pins and interfaces that we have broken out to our board, we will break them out on separate metallized holes. Important point, you need to fill the board with a polygon. I forgot to do this during the first shooting. Let's do it now. Press RMB, place polygon pour. We are on the top layer and let's draw the outline of the polygon. If we do not do this, the GND pins of our components will not be connected to the ground because they were not connected using conductors. And just all of the tracks will be floating on a bare PCB. We have filled in the polygon, now we must connect it to the ground. GND. Repour the polygon, right-click, Polygon Actions, Repour All. And as you can see, our contacts have been connected to the polygon of the ground. Let's do the same on the bottom layer. Or we can just copy and paste the polygon that we just made. Ctrl-C. And paste it here using this pad as a reference point. Now select the polygon that we just pasted. Transfer to the bottom layer and also connect it to the ground. So everything is green. Let's repour. And the board is ready. Saved. Let's check for errors. Tools, Design Rules, check. We have one error, something's not connected. So we missed the capacitor. Repour the polygon, and now the capacitor is connected to the circuit. Tools, Design Rules, check. Every time you make any changes in your design, all these tests must be performed. Now there are no errors left and the board is ready. On ST-Link, in addition to what we need, we have various lines and interfaces available on its external pins, and I decided to break them out separately on the board so that developers can make use of them. This is my extended version of the board that we are currently designing in Altium. Here you can see that SPI, I2C are also broken out on the center of the board. They are not present on the board that we are designing now as a team. UART, VCP. I did it all to give developers the ability to connect to these pins too and use them as their discretion. This is how my extended version of the board looks like. By the way, you can download the source code of the project in Altium, library components that we use today, scheme and PDF and Gerber files on the website docsflipper01, or follow the link in the description. What's left now is to send the board to production and see what happens. A few days after the video was recorded, I received the photos from the factory. This is what the final device looks like, and this is how it looks when connected to Flipper. There were also some flaws that we noticed only after it was sent to production. I forgot to connect the power detector. This problem has already been fixed on the version that is posted on the site. Bye everyone, and see you in the new videos.